We will talk now about graphs. Graphs are a generalization of trees. A graph is a pair of set of nodes of vertices and set of edges of arcs. There are two kinds of graphs, directed and undirected. They are quite different. We will also talk about how to represent a graph using an adjacency matrix, an edge list, or adjacency list. An undirected graph is a pair of set of vertices and set of edges. V is a set of vertices, E is a set of edges. The edges are unordered pairs, and each element is a distinct vertex in V. So we do not have a vertex from U to U, for example. Vertices are also called nodes. Elements of E are called edges or undirected edges. Each edge may be considered as a subset of V containing two elements. For example, VW in curly brackets denotes an undirected edge. We can also write it V dash 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 W or VW or WV. Because it's unordered, the order does not matter. We also say that an edge, VW, is incident upon the vertices V and W. A directed graph is quite different from a graph. It's also called a digraph. It's a pair of set of vertices and set of arcs. V is a set of vertices and E is an ordered pair of elements of V, which are called directed edges or arcs. For a directed edge, VW, which belongs to E, V is called the tail and W is called the head. And VW is represented as an arrow from V to W. So remember, V is the tail and W is the head. In text, we can simply write VW. A weighted graph could be a weighted undirected graph and a weighted directed graph. So a weighted graph, it's a triple, VW and E, where V and E is a graph, directed or undirected, and W, it's a function from the set of edges into R, the set of reals. Could be integers, could be rationals. For an edge E, W of E is called the weight of E. So, for the graph given as an example below, the weight of an edge from SF to SAC is 48. Because the graph is undirected, the weight of the edge from SAC to SF is also 48. We will see when we have directed graphs, edges connecting the same points may have different weights. If two nodes are not connected through an edge, then we say that the weight of the non-existing edge is infinity. For a directed weighted graph, we have weights on the arcs. So for the same example, from SF to SAC, the weight is 48, but from SAC to SF, we do not have an arc, therefore the weight is infinity. If the graph is directed, we define the degree in a different way than if the graph is undirected. The degree of a node would represent how many edges are incident to that node. But again, we will have a different definition for a directed graph versus an undirected graph. So if the graph is directed, we calculate the out degree as the number of edges going out of X, and the in degree of X will be the number of edges coming into X. So the degree will be the sum of the in degree and out degree. If the graph is undirected, the degree of X will be the number of edges incident to node X. Degrees are very important in determining the running time of an algorithm in a tree. Example of graphs. Graphs are everywhere. Roadmap is a graph, a directed graph. Computer networks are graphs. This is an example of undirected graph. Communication networks are directed graph. World Wide Web, undirected graph. Electrical circuits, directed graph. Task schedules, also a directed graph. If the graph is undirected, we say that A and B are adjacent if they are connected through an edge. So AB belongs to E. A and B are also called neighbors or adjacent nodes. In the directed graph above, we say that B is adjacent to A because AB is in A, but A is not adjacent to B because we do not have an arc from B to A. For two adjacent nodes in the example above, A is called the predecessor of node B, B is called the successor of node A, the source of the edge is node A, the target is node B. A path is a sequence of vertices from V, W1, W2, Wn, such that any two consecutive vertices, Wi and Wi plus 1, are connected through an edge. Each vertex is unique for a simple path, except the path may start and end on the same vertex, in that case will be called a cycle. The length of the path is the number of edges along the path. An acyclic path is a path where each vertex is unique. It's also called simple path. A cyclic path or a cycle is a path so that there are at least two vertices on the path, and the starting and ending vertex are the same because the path starts and ends at the same vertex. The distance from a vertex A to the vertex B is the length of the shortest path from A to B. If there is no such path, the distance between them is infinity. If the edges are labeled by a cost, a real number, the length of the path, A equal, and A is the starting point, which is x0, B is the ending point, which is sk, is defined to be the sum of the edge cost. So it will be the sum of xi, xi plus 1, where I equals 0 to k minus 1. In unlabeled case, so unweighted case, each edge is assumed to have the cost of 1. If an undirected graph has an edge between every pair of vertices, it will be called a complete graph. So in a complete graph, every two vertices are connected through an edge. A directed graph can also be a complete graph, but in that case, there must be a bidirectional arc or an edge between every vertex to every other vertex. A directed graph that has no cyclic path is called a DAG, a directed acyclic graph. An oriented tree is a DAG. An undirected graph is connected if there exists a path between every two vertices. So every two vertices are connected. If the graph is directed, we have the notion of strongly connected or weakly connected. A directed graph is strongly connected if there exists a path between every vertex, every pair of vertices. A directed graph is weakly connected if for every pair of vertices there is a path from the one to the other or the other to the original.